Question 2. A small stone A of mass 3m is attached to one end of a string. A small stone B of mass m is attached to the other end of the string. Initially, A is held at rest on a fixed rough plane. The plane is inclined to the horizontal at an angle of alpha, where tan alpha is 3/4. The string passes over a pulley P that is fixed at the top of the plane, and the part of the string from A to P is parallel to a line of greatest slope of the plane. Stone B hangs freely below P, as shown in figure 1. A coefficient of friction between A and the plane is 1/6. Stone A is released from rest and begins to move down the plane. The stones are modelled as particles, the pulley is modelled as being small and smooth, and the string is modelled as being light and inextensible. Using the model for the motion of the system before B reaches the pulley, write down an equation of motion for A. Well, with any mechanics question, I'm going to start by labelling some forces on this diagram, and there's quite a few to get through. So we've got attached to a string, so let's put tension in our string. Now the tension is going to be working away from our stone A and away from our stone B, so towards the pulley in both cases. A will have a reaction force, a normal reaction from the plane that it is resting on, so this R force is perpendicular to the plane. A's weight is 3mg, acting vertically downwards, where g is acceleration due to gravity. This will have two components, one perpendicular to the plane and one parallel to the plane. The weight of B is mg, again working in a vertical direction with g being acceleration due to gravity. The coefficient, I'm told, is 1/6. Because I have tan alpha is equal to 3/4, which is my opposite over my adjacent, I can write the rest of my Pythagorean triples. So sine alpha will be 3/5 and cos alpha will be 4/5. I'm told that A is moving down the plane, and so acceleration is going to be acting down the plane for A and upwards for B. And then finally, because A is moving down the plane, the friction is going to be working against A, so friction will be working up the plane. So now I can start looking at part A, writing down an equation of motion. So the equation of motion is F equals ma, which is my resultant force is equal to mass times acceleration. Now the resultant force for A is the forces acting down the plane, which is going to be 3mg sine alpha. It's this component here. And that's going to be opposed by friction and tension. So I've got 3mg sine alpha minus friction minus tension. That's my resultant force is equal to mass, which is 3m, times acceleration, which is A. And so this is my motion for A. I don't need to do anything more with that at this point. Part B, show that the acceleration of A is 1/10 of g. Well, we've found an equation of motion for A, so let's find an equation of motion for B. Now, the equation of motion for B is its resultant force equal to mass times acceleration. B is moving upwards, so its resultant force is T minus mg, and that's equal to its mass, which is m, times acceleration, A. So I have something I can substitute for T, but I can see that I would like to be finding friction at some point. So in my mind, I'm thinking, well, friction is mu, which I have, times R, but at the moment I don't have R. So let's look perpendicular to the plane. So resolving force is perpendicular to the plane. The force is outward, which the only force is R, is equal to the force into the plane, which is this component of the weight, which is 3mg cos alpha. Cos alpha I know to be 4/5, so I can write R as 3 times 4/5, which is 12/5, and that's mg. As mentioned, I'm finding R to be able to make some substitution for friction. So friction I know to be mu times r. I know mu to be 1/6. I've just found r to be 12/5. And so I can find friction to be 2/5 mg. I now have something for friction and a substitution for tension. So I can rewrite this equation in terms of mg and a. So substituting in the values I've got, 3 mg sine alpha is 3/5, so 3 times 3/5 is 9/5. So I have 9/5 mg minus friction, which I've found to be 2/5 mg, minus t. T, of course, is ma plus mg, so that's minus ma minus mg, and that's equal to 3ma. This equation now can be simplified. I can divide the whole thing through by m, and I can bring my g's together. So 9/5 take away 2/5, take away 1 is going to be 2/5 g. Adding this ma gives me 4a, and then dividing through by 4 gives a is equal to 1/10 of g, which is what I wanted to show. Part C, I want to sketch a velocity time graph for the motion of B from the instant when A is released from rest to the instant just before B reaches the pulley, explaining my answer. So let's start with our axes. So this is a velocity time graph. So velocity on the y-axis, time on the x-axis. When this stone is released, it is going to start accelerating, and it's going to have constant acceleration. And that's going to cause the velocity, which initially is at 0, to increase. And so I have this line where the velocity is increasing with respect to time. And this line must be straight because I know that dv by dt, so the change in velocity by time, is acceleration, and I know my acceleration is constant throughout this motion. In reality, the string is not light. Part D, state how this would affect the working in part B. Well, if we look at the diagram again, if this string has some weight to it, then it's going to have more of an effect here on stone B, where it's pulling down, than it is going to have on A, since it's on a slope, on an incline here. That effect will change the tension in the string. And so the tension at A and B would be different if this string was not light.